morning. I hope I can still say good morning. Good morning, everybody. Welcome to this presentation on the elimination of hidden black boxes in machine learning models. My name is Ingo Mierswa. I'm the founder of RapidMiner. RapidMiner is one of the leading platforms in data science machine learning. I'm doing this stuff for now 20 years, and I've seen it all. And I would like to share today with you, well, first of all, there's a description of the problem about understandability and the lack of understandability in machine learning. More importantly, I would like to share a couple of pieces of advice how you can overcome this. But then the most important thing is going to be, I will introduce the concept of hidden black boxes to you. And that's unfortunately a problem. Most people are not even aware that it is existing. And the good news is, it's actually easy to fix, and you have to fix it. So stay tuned. We will end on the hidden black box. But before we get there, let's actually phrase the whole problem in a slightly different way. This is a quote I took from the Gartner's Magic Quadrant of Data Science and Machine Learning Platforms research piece. 60% of all models which are intended to be put into production are actually never operationalized. And this is just an astounding number. Think about this. I mean, it's not 60% of all the models, but models which actually should have been put into production. And 60% of them are never seeing the light of the day. What does this really mean? A model which is not put into production provides zero value. Why bothering building it in the first place? So this is a huge number, and it really annoys me actually, because creating those models is a lot of work and then nobody's using them. So what are the main reasons for this? Well, Gartner cites a couple of reasons. First reason is a bit technical, and it makes kind of sense. The first reason is, well, maybe there's not a good set of tools to support the operationalization. And I would agree, especially if you're coming from a more coding-centric approach to data science with R, Python. This is all good and fine, but it is, in fact, a little bit problematic to take those models and put them into production. I would argue, though, that if you're smart enough to actually build a data science and machine learning model using, let's say, Python, you're probably also smart enough to overcome those technical hurdles somehow. So I think the other reasons, which are less technical, are more important. So the first thing is, unfortunately, in data science, since it's very complicated, there's a lot of math involved, a lot of specialists, PhD statisticians, who all put somewhere into the basement and go and create some models. They often do this a bit in a silo. They're a bit disconnected from the rest of the organization. And that's too bad, because what this typically means is that the stakeholders in the business are not really part of the model creation process. They don't really understand what this model really means. All they get back is complex mathematical formulas, and then, well, good luck. And that, in particular, really leads to this lack of understandability, and as a consequence, then, to a lack of trust. And I personally think this is the biggest issue we have in data science as of today. So if you're not trusting what I'm getting back as a result, how could I actually really disrupt my business? How can I change my business process using machine learning models if I hardly understand what this thing is doing in the first place? It's like hiring somebody, solving a problem. Unfortunately, this person speaks a different language. I don't understand anything. Okay, sure. Do you understand what I want you to do? Some answer. You not understand anything? Are you feeling good about that? Probably not. So how do we really solve this problem of lack of trust in machine learning? And I would like to give you an example. I'm going to use a couple of different data sets in this presentation to illustrate the different techniques to overcome this huge problem. And the first data set is literally very close to our heart. It's a data set about heart disease, which is, well, in general, cardiovascular diseases are the #1 cause of death in most countries in the world. So it's definitely a serious problem. And why is this important? Why would it be a good idea to have a machine learning model which can be used to predict if somebody's more likely to suffer from a heart disease down the road? Well, because you still have some time. You have still the chance to change your lifestyle, maybe your diet, or take some medication. But if it's too late, well, it's too late. So maybe it would be a good idea to create this model, so let's try to do this. So this is the data set, and it's not important that you understand all the details, but please still follow along a little bit. So on the left side here, those blue-white columns, this is data columns describing our patients. So we also call those attributes or features or variables. So we have things like age of the patient, or gender, or if there's a certain type of chest pain, or what is the resting blood pressure, for example. So we have those columns on the left, and then we have 303 rows. Those are our patients. So for every single patient, like the first row here, we have a 63-year-old male with a typical angina chest pain type, and so on. And then there's this column here on the right, this orange one. This is what we call in machine learning a target, or also a label. This is what we want to predict. I mean, just for the few of you who have really never building machine learning models, this is kind of like a machine learning model 101 for you now as well. So the goal here is that we take information in those blue-white columns here on the left and create some mathematical model or a formula which can be used to predict the outcome on the right in the orange column, or at least the likelihood of it. So you could create, for example, rules like, well, if you have a 40, or let's say if the age is higher than 40, and you're a woman, and you have a resting blood pressure of 300, yeah, you're very likely to suffer from heart disease soon. I mean, I guess very soon. So that is the idea. So coming up with this kind of rules. And a rule would be simple because we can understand this, but we will see in a second that life is not always that simple. So let's actually build some models together. Obviously, since I like it a lot, but I might be a little bit biased, I'm going to use, give me 1 second. I am going to use, here we go, RapidMiner for this. And in fact, I'm going to use RapidMiner's auto model. So because it allows me to build, I don't know, 10 different models in the next 20 seconds or so. So this is the same data set we have seen before, just loaded into RapidMiner. Only difference here is the column we want to predict is here on the left, so I just selected this. And now RapidMiner goes and creates a couple of columns. So just ignore the next 2 steps. Same here, all I'm doing here is basically telling RapidMiner what columns to use. Everything which is green is fine, so that's good. And now RapidMiner suggests a couple of machine learning models, like simple models like linear models, second from the top, or a decision tree further down here, but also more complex model like gradient boosted trees, deep learning, stuff like that. I could turn on automatic feature selection here on the left. I just don't do this in the interest of time. Keep in mind, whenever RapidMiner is now trying a different model here, we're actually not just calculating one. Let's say for the decision tree, we try different algorithms, we try different parameter settings in order to find the best model for you. And if you turn on automatic feature engineering on the left, it can easily end up that we create like between 100 and 250,000 models for this one data set. That might take an hour or so, so let's maybe speed it up a little bit, not turning it on. In this case now, we should actually be done in a couple of seconds. So first results are coming in. The first model we calculate here is a so-called naive Bayes model. It has an 86% accuracy. Then the linear model, 88%, logistic regression, 83%, and so on. Ooh, decision tree, look at that. Doesn't really look very good, 62%. Well, let's actually have a look at this model, because decision trees in general are something people say they can understand. And if I look at this model here now, I would say, yeah, most of us will be able to follow along. I mean, this model is only using 2 of the input columns. ST depression, whatever that now means. I hope there's no doctor in the room because I might actually say wrong things about patients here. Correct me if I'm wrong. But then there's also the maximum heart rate. But this whole model, it's maybe too simplistic. Yeah, it's easy to understand. Would I trust my life to this model? No, probably not. I don't know. If that's all doctors are doing, that's probably too simple. Let's try a different model, though. So if you have a look here into this table, so now all the models are done, we see that actually a linear model is also pretty good, gradient boosted trees as well. The problem is with gradient boosted trees, though, although they are still tree-based, you now end up with like dozens or hundreds of those models, so they are not really easy to understand. We will come back to them a little bit later. But linear models is something many people believe they can understand. Well, at least you can sort the coefficients here to see what are the coefficients with biggest influence, so like the max heart rate, or even the gender has some influence, or if I look at the other end of the spectrum, well, this asymptomatic chest pain type, that seems to be important. But now let's be really honest here, as a group. So we can see what is important. Who of you does really know how this model actually creates a prediction? I mean, truly know. We all believe we understand linear models, but what is the formula? Feel free to raise the hands. Not so many at the same time. 1. Thank you. 2. That's the problem. It seems to be simple, but actually even that model which performs very well is no longer that simple. And this, unfortunately, is not always the case, but in general is a bit of a rule for machine learning that the better the models are, the more complex they get. And even a linear model can actually already be too difficult to fully understand. And let's not even try to understand like neural networks or other stuff. So that is the situation we are in. Bless you. That is the situation we are in. The good models are too complex, so we can no longer understand them. And the bad models, which are not performing very well, they're easy, but we don't trust them because they're not good enough. So we would like to get better models, but the problem is if all I see is I put some input in on the left side and I get some output out on the right side, the inner workings, they stay hidden from me. I don't understand them. That's why we call those models black boxes, because we can't really understand how they work. So how can we overcome this problem? It's actually quite simple. Here are 3 pieces of advice, and I will explain all 3 of them to you now. The first one is, I really believe you should focus much less on prediction errors alone. Unfortunately, most data scientists are really trained to do exactly that. Let's build more accurate models. And there's nothing wrong with this per se, but I think you should balance this also with the understandability of the models. And I will show you a different data set and some examples on the next couple of slides. Another idea which is underused, unfortunately, is to take the model and put this into some simulation framework so you can actually play around with the model, see how it works, and more importantly, you can confirm your prior knowledge. Whatever you believe to know about your domain, you can actually confirm if the model behaves like you would expect it to behave. Again, another example a little bit later. And then if you do this at a larger scale, this actually leads to a technique we call local explanations, and that will become a bit clearer a little bit later as well. So let's start with number 1 here, focus less on prediction errors. And I would like to introduce a different data set because it's even simpler than the heart disease data set. So this one here. We have only one dimension, x, on the x-axis, and a second dimension, y, on the y-axis. And the goal for the machine learning model here is to predict the value of y given any value of x. This is what we call a regression problem, as opposed to the classification problem we have seen in the heart disease, where we had 2 classes, yes and no. So, quick example, if I know the value for x is -5, then the model should say something around 10K as the outcome. Okay? Pretty simple. So obviously this is a nonlinear problem. And there's also some noise involved, and there's this strange little peak here at the center. So I'm not expecting that the linear model is doing a good job, but nevertheless, let's try. So if I put the linear model on this data set, the red curve here, well, we can see a couple of things. First of all, there's not a lot of noise, which is good, but it just didn't get the shape at all. And as a consequence, well, I said, let's not focus too much on the prediction error, but at least let's calculate them. The error rate of that model is horrible. So it's a 39% relative error, so not really good. Well, if a linear model is not good, let's maybe try a nonlinear one. For example, this decision tree. They can be also used for regression problems like here. Well, then they're called regression trees, just for information. We can see, well, it's getting the overall shape, which is good. But there's a bit of noise here. You see those little red dots, they're all moving around. Doesn't make a lot of sense there. And it definitely struggled with the peak here at the center. I mean, what are those flat lines here? And then there's just this random blob there, up there. It just didn't really fully understand the data. But the really good news is it's doing a much better job. So the error rate dropped down to only 6%. So I mentioned the gradient boosted trees before, which is a technique, boosting in general, to learn from previous mistakes. So you start with one tree like this one, and then you build another tree focusing more on the areas where the first tree made more mistakes. So in this case, for example, more on this area here. So you really focus down on this local area there. And then after you build the second tree, you build another one which tries to focus on the mistakes from the previous two, and so on. So you stack them up all on top of each other. So that's the basic idea of boosting and also of gradient boosted trees. So if I do this, look, small difference, but important. Look at that. So less noise, it got the peak as well, and the error rate was going down to 4%. Fantastic. So I think we nailed it. Good model here, right? Clear case as well. We have 3 models. Gradient boosted trees, clearly the best performing model, only 4% error rate. Then we have the decision tree, 6%, and a linear model with 39%. So it should be totally obvious to us that we go with the gradient boosted trees with the smallest error. Let's put it into production. Let's make some money here. Not so fast. Let's actually have a look at the model itself. So this is the linear model. And we can all understand that. It's the prediction of y is calculated with 817 times x plus 17,000 something. And while this model was not in particular good, at least we can learn something from that. I could, for example, learn, well, if I double the value of x, so times 2, I increase the value of y by roughly 1,600. So at least I learned something. I can take some information out of this. So, but decision trees are supposed to be understandable as well, right? And they are so much better with 6% error rate. So let's have a look. This is the tree. In case you wonder, what is this white blob there? No, this is the actual tree for this data set. And since you can't hardly read anything of this, let's just zoom in onto this right area here. That is just one tiny part of the tree. Look at all those little splits for x. Well, if x is larger than 16, then check x if it's smaller than 16.7. If it's then larger than 16.5, then it's supposed to be 295. Is there anything I can learn from that tree? No. I mean, look at the whole tree. There's nothing for me to learn from. I don't understand how this tree is working. I don't trust this thing. So yeah, it's a much lower error rate, but it's hard to understand. And with gradient boosted trees, it's even worse because now I don't have a single tree. I have 500 of them. And they all depend on each other. Forget it. I do data science for 20 years. There's no chance on earth I could understand anything of that or learn from it. So what are we doing then? I would like to use this linear model, but it's just not good enough. And the gradient boosted trees are good, but I don't understand them. So maybe there's other ideas. And here's the second piece of this piece of advice here. This is another model, the red line I created. And this looks pretty good, right? I mean, hardly any noise. It got the oval shape. It got the peak. It's not really perfect there on the far right end, though. But overall, it looks good. Well, what did I do? Did I use some neural networks, deep learning, or just voodoo and magic? Nope. It was a linear model. But I used automatic feature engineering, also part of Rep-and-Minder's auto model, to create a couple of additional columns based on x, things like absolute values of x, squared value of x, stuff of that nature. And if I do this, I can build a linear model on those additional columns, like 5 or 6 of those, and that model actually gets the whole shape here very well with a pretty good error rate. But look at this model. Now that I can read it, it's 10,000 times absolute value of x plus 7,500 times x absolute value of x squared. And then 700 divided by absolute value of x, which, by the way, explains the peak in the center. So let's just assume this would be data from some physical process or manufacturing process. I, as an engineer, for example, could look at this as a domain expert and say, yeah, that might make sense. I can, oh, it's squared. Oh, interesting. So I learned something. Or I can say, yeah, I kind of guessed it was squared, but I didn't know that this would be the coefficient. So I trust this thing because I understand it. So the takeaway here really is, don't just look for the best model in terms of accuracy, but actually balance this with understandability. And you can actually be a bit creative, and if you are, you can get very, very, very far with even very simple model types like this linear model. And I would absolutely sacrifice this 1% of error rate and use this model, which is much easier, doing a much easier job to actually instill and create some trust. So that is the first section on, like, don't focus too much on prediction errors. So let's move on to the second one, which is about using the idea of simulation around machine learning models. Well, what do I mean by this? So let's just assume we don't have a linear model, but something we don't understand at all. It's truly a black box. We have no chance to understand how it works. But we do understand if we feed in some input here on the left, we can expect some output, and we have some knowledge about our world. So for example, I could be a doctor. Let's go back to the heart disease here. And I could say I have this 54-year-old woman with asymptomatic chest pain, with a colored vessel rate of 0.7, whatever that means, and a max heart rate of 143, and other information. And I, as a doctor, could, for example, say, like, you know what? I would say, too bad, but I have bad news. It's very likely that this person is really going to suffer from a heart disease. And so my expectation is, yeah, should be a heart disease case. So I can feed something into the model, and I can see how the model reacts. And then I can check if this matches my prior expectation. And if I do this for 10, 15 cases, I might build enough trust to say, like, yeah, that model behaves pretty much like another doctor. I like that. That's good. So this is now going to be a little bit hard for us because I assume there are no doctors in the room. But there's one thing we believe to know about heart disease, I mean collectively, all of us, and that's that high levels of cholesterol are not a good idea. Let's try and use our model actually and check for this hypothesis that if you increase the cholesterol level, that actually that should also increase the risk for heart disease. So let's go back here. Let's go with just the first one here. It's a knife base, which is not super hard to understand, but most people probably wouldn't be able to understand it. So here we have the simulator. On the left side, you have the inputs for the model, and we can play around with this in a second. And on the right side, you see what the model is going to say and how likely this outcome is going to be. So for the inputs, which is basically your average patient, good news, for average patients, the likelihood for suffering from a heart disease is only 14%, and it's an 86% for not suffering from this. On the bottom here, you see actually the main reasons for this particular decision, but we will come back to this a little bit later. So here we have now our cholesterol level, and let's play around a little bit with this. So while I move this around, you see on the left side how this current value, the orange bar, behaves compared to all the values we know from our training data. If I bring this down now by moving it to the left side, pay attention to the blue bar on the right, so it actually drops the likelihood for heart disease a little bit. But if I move it up, let's bring it up and further up, you see that this actually has some impact on the likelihood for heart disease. It goes indeed up. And if I crank it up all to the right, I have pretty much a dead patient. So Again, we are not doctors, but we believe that this is something we know about heart diseases, and we checked it with this model, and it behaves exactly like we would expect it to behave. So even if I don't understand the model, at least it helps me to understand how the model works and if it behaves kind of like a human being. So that can be helpful, sometimes at least, to instill or create this level of trust. But at the same time, I think this kind of simulation is a fantastic tool also for using machine learning models in the first place. So yeah, machine learning is great if you automate decision making. But in many cases, you actually want to offer something to a user, to just like an analyst, so they can play around and see what happens. Well, let's double the price for this product. What is this going to do to my conversion rate? Well, let's reduce our service level for this group of customers. What about our churn rate? So using a machine learning model by actually trying to figure out what is the best course of action to get to the desired outcome, simulation is a fantastic tool to achieve that, next to also creating this level of trust. So then, okay, we did this now with playing around with one input dimension here. What about the others? So what is really driving a single decision? In order to figure that one out, we can actually do this a bit at scale. And I'm using a third data set now to explain this whole idea. So here we have a two-dimensional data set, X and Y, and it's a classification problem. So obviously we have two classes, green and blue. And it looks simple for human beings, I guess. It's kind of this checkerboard pattern here. But for example, a linear model would fail with that data set. I mean, there's no linear curve I could put into this plot here to separate green from blue points. All right, so let's go with our good old friend, the decision tree again. And this is the tree for this model. And I guess most of us would think, well, that looks already more complex than you expected it should look. And the reason is because, well, we human beings, we just look at one corner like this one here, and we just say like, well, if the value here is higher than that and smaller than that, that is really easy to explain why this is a green corner. But the tree needs to cover all the cases at the same time, and that often makes models more complex because they really need to look at all the data points at the same time. So let's also focus just now on one data point. Let's say this one here. Obviously, I hope, this is a green data point. So if I would ask you now, out of the two dimensions, X or Y, which one is more important to motivate why this is a green data point? Is the value of X more important, or is the value of Y more important? What do you think? You said X. Thank you for playing. This is wrong. But still, thanks. Y is more important. Why is that? Because if you change Y a little bit, if you go a little bit up, it actually changes the class. So it has more impact on the decision if it's green or blue, versus X, if you go to the left or right, it really doesn't matter a lot. It always stays green. So if I look, for example, at this data point here on the left side, it's exactly the opposite. Here, if I move the point up and down, it has pretty much no influence on the decision if it's a green data point. But if I go a little bit to the left, it turns the class over to blue. So in this case here, X is more important. So let's go back to the first point. Now we can actually do this at scale. And that's the same thing as the simulation. So if I want to explain what really, or how is the model coming to a conclusion for this particular data point, what I can do is I just generate in the neighborhood of this data point more data points artificially. I ask the model, what is the prediction for those data points? And then I check for every of the potential input dimensions, which of those dimensions actually has more influence of the prediction value of this data point. And we could clearly see in this case here, well, Y has a much more influence for this neighborhood here than X. So Y is contributing more to this prediction. It's supporting the prediction stronger than X. And this idea, as simple as it might look, is actually not that old. There is an algorithm called LIME, Local Interpretable Model Agnostic Explanations, and it was only published in 2016. And so you saw that actually in our simulation before. So all the green bars mean they are supporting a prediction like yes, and the red bars mean they are contradicting, and bars which are not even, or input dimensions which are not even in this plot, they don't add at all. So in RapidMiner, we actually created a different variant of LIME, which works on both numerical and categorical data for classification and regression problems, and also in real time. For that reason, I can actually play around like I did with the cholesterol level. So right now, it's actually supporting the prediction of yes. But if I bring it down again, it becomes less important. It kind of drops out, but you can see how the other bars are moving around. So being able to calculate this in real time is pretty important for the simulation, but you can also do this for all the data points at the same time. So here you create all the predictions, and dark green means it's supporting the current prediction, and dark red means it's contradicting the current prediction. So it's really an easy tool to also explain why a model comes to a certain outcome with using this little technique. So here you have it. I actually have a tooltip here, which I don't want to have. Here you have it, the 3 pieces of advice, how to overcome this black box nature of machine learning models. But there's one more thing, and that's this concept of hidden black boxes. The problem really is, let's say you saw those models for heart disease. They have like 85, 87, 88% accuracy. You like that. By the way, doctors have 82. You have that. You have been playing with the simulation. You created a linear model, which is easy to understand. You built enough trust. You want to put it in production. But there's one thing you don't know. You have no idea how I actually created this model. Yeah, I used RapidMiner Auto Model. I pressed 5 buttons. But what did I do to the data? How did I optimize the model? How did I validate the model? You don't have any idea what it is. For all we know right now, this model could have been the output of some random process, or potentially even more dangerous, a faulty one, where I was leaking some information about my data, where I wanted to validate the model, how good it performs, and I was accidentally leaking it into the training data, which is an absolute no-go in data science. So how would you know? I pressed a couple of buttons. I mean, I love RapidMiner, but do you trust me? I mean, am I that trustworthy? I don't know. So I am. So I actually have another model for you. Let me actually show it for you first. I go back into a different part of RapidMiner, this process designer here. So I load the same data here, but then I do some magic inside of this box here. I'm not showing you exactly what I'm doing, but like an auto model, I'm actually, so same data as before. I'm running this whole thing, and I will show you the performance. So we have roughly 94% accuracy, so that's much better than the other models. And it's a linear model again, using only a few coefficients, so this is fantastic. We have a better model with a higher accuracy. For comparison, the best models have been like around 87, 88% before. High understandability, thanks to being a linear regression model. This is fantastic. I am not a doctor, but if I would be, I'd go into production with this, I use it on 1,000 patients, and I just killed 100 of them. That's bad news. What happened? Well, I actually, if I now show you what I did, and I'm not going to the details because I don't have the time, but if you're interested, I can discuss with you later on. I made a couple of mistakes. I didn't really correctly validate the impact of my data preparation, which is something, unfortunately, many, even trained data science are doing wrong, and pretty much all automatic machine learning products are doing wrong as well. I then did feature engineering, but unfortunately, when I did this, I only optimized for accuracy, and I was using information I shouldn't have been using. And then I made a third smaller mistake while I was validating the model. So the interesting thing is, if I fix all those problems, so the same process before, but I just fixed the problems, and I run this again, this takes a second, but what we see now is that the model we thought has 94% accuracy, in reality, actually has 83. So it's 10% less. That's why I said, if I use this model on 1,000 patients, I could just killed 10% of them. And that is not acceptable, obviously. But that's what's happening. People trust those model building products, and they just say, okay, fine, but you don't know how the model was created. This is what we call the hidden black box. You need to be able, at least, to see all the details. How was the data prepared? How was the model optimized? Was the data preparation actually correctly validated as well? Most automatic machine learning tools are not doing this, and most citizen data science don't have enough experience to really question those results. So this hidden black box is never acceptable. You can play around with simulation like all day long. You can see all those accuracy values, but this is the dangerous thing. If you validate it incorrectly, the models actually will look better, and the only point in time you will find out that it fails is after you put it into production. Again, not acceptable, never. Obviously, the solution is pretty simple. Even if you create a model like this, just have a functionality that you can open a process like that. Even if you're a citizen data science who are not able to check all of this, maybe somebody else in the organization can do this for you, like a quality assurance check, so you can be on the safe side that you're not making stupid mistakes. So a couple of key takeaways here. First one, reduce your focus on errors. Just don't try to optimize only for them. Balance it with understandability from the beginning. Explain models. You should spend as much time on explaining models than on creating them. If you actually spend more time on creating them, you're over-focusing on prediction errors to begin with. You should really make sure that people can follow along, that business stakeholders really understand what's going on, because otherwise the model will never go into production. And what's the point about having a 0.1% more accurate model, which is not in production because the value of that model is 0 and not higher? So that is a no-go. And the last thing, which is an even bigger no-go, you have to avoid this hidden black box. I love automatic machine learning. We at RapidMiner do love automatic machine learning because it makes data scientists more productive, and it makes actually possible for citizen data scientists to actually build machine learning models in the first place. It's fantastic, but only if you're not allowing the introduction of hidden black box, because otherwise it's worthless. So make sure that you're doing it right there. We try our best to do it right, and we are really grateful to all our users, customers, but also Gartner to recognize us for that. So now for 6 years in a row, we made it into the leaders quadrant of this Magic Quadrant for machine learning and data science platforms. That's a fantastic result. We are really grateful for that. And I'm also very, very grateful for your attention today. Thank you very much. Visit us at our booth.